Hi, everyone. We're going to go ahead and get started. So I just want to welcome everyone to the Hive user group meetup at Cloudera. Really excited to see everyone here. We got a lot of really interesting talks. It's great to see all the community engagement. We've got a pretty packed agenda today, so we're going to go ahead and get started. Just so everyone's aware, there is guest Wi-Fi. So if you need Wi-Fi access, the login and the password are right there, and there's signs everywhere in case you forget. So I'm going to briefly go over the agenda. So the first half of the meetup, we're going to go over some lightning talks. So each lightning talk is going to be 10 minutes each, which includes Q&A. So each talk is going to go pretty quickly. I know that doesn't leave that much time for Q&A, but hopefully some of the speakers will be around later on if you want to talk to them in person. So these are all the lightning talks. Unfortunately, one of our speakers had a family emergency, so he couldn't make it. And then after the lightning talks, we're going to have a panel on the Hive Metastore. So this is something I'm really excited about. We're going to go over various topics that are going on in the community for improving the Hive Metastore, Hive caching, and we're also going to talk about some kind of long-term vision for HMS and kind of where it's going in the future. So without further delay, we're going to go ahead and get started with our first speaker, Shei-Fu from Uber, who's going to be talking about Hive on Spark. Every time you want to change slides, just let me know, and I'll change them.
Awesome, thank you. Good evening, everyone. I'm Xue-Fu, and I think pretty much it's like in every meetup, our user group meetup, for Hive users. So last year, if you were here last year, I talked a little bit about like how Hive was used at Uber, and what's the major initiative were about like move Hive on Spark to production. So today I'm here sort of giving like updates on where we are on things, and something that we are currently working on, and something that we are looking forward to. Next slide, please. So this is just an agenda as I will quickly go over. So see, we talked about like the scale. Of course, Uber is a big data company. We have a lot of data. I like to give a sense of how Hive is able to handle such a scale, and then talk about like the Hive on Spark initiative and how what's the current status. Then followed by like the results when we move the Hive on Spark into production. What do users see? Then one major effort that we are spending on is about the efficiency work. So Uber is a company where they talks about it's purely about efficiency. We manipulate data, like we get the sense from the data, but the goal is to make money. How? But operating efficiently, that is one main approach. Then I will have summarize my talk. Next slide, please. So here's our scale. For Hive, we have over 1,000 like active Hive users, and the weekly query is about like 300K per week. And our data, we have a data lake that's about 31 petabytes. That's unreplicated data lake where Hive is one of the engines that to be used by the user to access the data. And our Yarn cluster is over 2,000 nodes. The use case are pretty much covers all sort of like the SQL on Hadoop, like ETL ad hoc queries as well as dashboarding. Next, please. So I'm happy to share that we have completed the Hive on Spark migration, and right now there are about 92% of queries. This is actually it's not right now, but this is the data all the way back at the beginning of this year. So over 92% of queries that's already running on Hive on Spark. The rest is mostly on MapReduce. It's for a big company, it's harder to get everybody to migrate. So there are still some left over. Hopefully one day when we deprecate the MapReduce, they have to move on. And test traffic, there's close to zero. There are some. I think there's a few queries that's still running on test, but hopefully we can also migrate those. So with this effort, the achievement that we have is our Yarn computing, is purely about Spark. So Yarn workload is a Spark workload. We don't have MapReduce or we don't have map tags. So that's consolidate our tech stack. And also right now we are focusing on the Spark efficiency, which I'm going to talk next. So the result we see with these efforts, we have better performance and better efficiency, and also it's more HDFS name node friendly. So next, please. Of course, there's also on the operation side, we want to consolidate our tech stack and reduce the support workload, also make it efficient, our efficiency work more impactful in the sense that we do one thing, like we improve Spark efficiency, our whole cluster utilization get, like the utilization and the efficiency get improved. So, what are the challenges for Spark efficiency? Of course, there's Spark efficiency. If you know about Spark, there's two main allocation schemes. Static and dynamic. So static is pretty bad for resource sharing and efficiency. And the dynamic allocation is better, but it still have a lot of efficiency problems. For example, in the earlier versions of Spark, like the version we are using, it has a minimum idle time, like 60 seconds. If you go lower, your job can fail because of the internal issues. And also, Spark, like running tasks, like small tasks, they actually say that they favor smaller tasks, but it's probably good for Spark, but actually it's pretty bad for efficiency. And also in our operations, user sometimes, when they do static allocation, they forget about to shut down their application, so the containers running around and prevents others from using it. And of course, there's also like a fixed executor and the driver sizing. So you can, at the static, when you launch your application, you give those params, and the size cannot be changed. Regardless, like you have a big query or small query. Next, please. So we did a bunch of things, but there are mainly two major things that we did that make a huge result, which I will show next. But the two main things are, the first is allow zero idle time. So there are a couple of Jiras that's about this. So we backport to our version 1.61, and it make a big difference. And also task per core, that's about the task size. Because the task run is small, it runs pretty fast, and the executor comes up and then shut down. So that has some overhead. So we want to let the executor to run more tasks before it go away. So that's the attitude about. Of course, because our version is so old, so we have to backport a lot of other patches that those patches are relying on, or because of the code conflicts. Next. All right, here's by doing those two simple things, if you look at the Jiras, it's just a few Jiras, but the improvement is pretty impressive. look at there's a dip on that side. Like 3 weeks ago, we turn on those improvement for our workloads. So we see a dip at the right end. So this is the average query week core consumption. So that's got to reduce a few times. I think probably 4 times, something like that. Next, please. Query elapsed time. So this is the latency that the user see. You run a query, right? You get the result. That's the whole elapsed time. So it also have about 3 times improvement. So this is the average query for we average the query out. Next, please. So if we see the percentiles, the P95 week core consumption, you can also see a similar, even a bigger dip by doing those sort of simpler things. And the next, for the elapsed time, you see it also about 3 times latency reduced. And the next slides will show you that for the untreated traffic, so the traffic that's not treated, and you see the pattern that you don't see a dip, right? There are some sort of improvement, probably because the some traffic are utilizing less resources, so those pairs may benefit from that. Next, please. So the elapsed time you see is a completely sort of normal pattern, but there's no dip. Cool. Next. So future work, so we like to do more on the efficient side, like driver efficiency. So driver sort of rational driver is not that efficient, and sometimes it has give even stability problems. And executor and driver sizing, as I mentioned earlier. And also we want to have some internal utilities or some sort of centralized server to guard those Spark applications so that they want to be run away. Of course, we want to improve Hive efficiency itself. We have the community made a lot of progress in that, like includes like Parquet vectorization. So we may brought this in by upgrading our Hive and gain those benefits. I think this is pretty much my content. It's simple, but hopefully this help you to when you have a similar efficiency requirement, especially when you move your workload to the cloud, right? You want to utilize those resources less so that you pay less. So I think this is probably useful as a reference. As a summary, we have completed our efficiency work, migration work, and we consolidated our tech stack. And Hive on Spark can actually run at a Uber's scale. And we also, by doing this, you also have the room to improve your efficiency. And similarly, if your efficiency improves, and your latency actually also get improved. Yeah. Great, that's what I have. Thank you. Any questions? Do I have time? Sure. Yeah.
Have you run across any queries or features in Hive that don't work with Spark?
No, so I don't think the feature should be completely compatible. You don't have to use switch engine. There's no feature limitation because the plug-in level is not at the query planning. These are shared. Like even the map side, reduce side processing is completely the same. Is there any query that cannot run? I mean, we have some queries that need some special treatment. Like sometimes you need to have to tune those parameters to make it work. I would say majority, maybe even more than 99% of queries that can run Hive on Spark. There are some, I mean, some are easier to migrate, some are sort of difficult, but it really needs some tuning. Yeah. Cool. There's one more question.
Sorry, I just have a simple question. Could you, what's your definition of efficiency?
Yeah, do you mean more like parallelism with the resource?
Right. Efficiency is the resource utilization. It's about the memory and the vCores, the CPUs. So we want to, for the same query, want to reduce the footprints for the two, like CPU and the memory.
I was going to ask if you are planning on contributing the patches for Hive on Spark upstream back to Hive.
I think that all the patches are in. Okay, so there are two things. Those improvements, if you see the Jira, they are Spark Jiras, right? So Spark Jiras, Hive on Spark depends on a particular version. I mean, each Hive version depends on a specific Spark version. Right now, it's coupled. So if you stick with that version, so you got to backport those patches, right? It's the same patch everybody sees. And so for all the Hive improvement, today I didn't mention anything about Hive improvement, but when we do things, we absolutely will contribute to the community first. That's always our practice. Great. All right, thank you.
Hi, everyone. So I'll be the next presenter. So my name is Sahil. I'm a software engineer at Cloudera. And today I'm going to be talking about Hive on S3 performance. So a brief agenda. Basically, I'm going to give a bit of background information about what S3 is and why Hive on S3 performance is challenging. And then after that, I'm going to talk about kind of how historically Hive on S3 has worked in the past, how it works today, and then I'm going to wrap up with some future improvements that we have ongoing in the community for improving Hive on S3 performance even more. So what is S3? So I'm assuming most of you guys all know what S3 is. It's a storage service managed by AWS, Amazon Web Services. It's an object store. It has some very nice properties. One of them is that you don't have to manage it yourself. It scales horizontally very well, and there's no single point of failure. The diagram on the right shows kind of a very high-level overview of how Hive and S3 interact with each other. So instead of storing your data on, say, HDFS, a lot of users are starting to store their data on S3. And this is becoming a more and more common pattern as more users move their Hive workloads into the cloud. So what's the big deal? Why is Hive on S3 performance so challenging? And the reason is that while S3 has a lot of nice properties, those properties kind of come at a cost. There are certain characteristics of S3 that make performance very challenging. And the three biggest ones that Hive are concerned with are, one, is that files are immutable and you can't actually rename files. And this is in contrast to HDFS, where you can append to a file and you can also just rename a file using like a simple RPC call to the name node. The next main challenge is that metadata operations are very slow on S3. And this is especially compared to HDFS, where like listing a bucket or getting the file status for something on S3 could take up to a second. So if you have a Hive query that is maybe scanning thousands of partitions, that can take a really long time. The third major issue is that S3 is an eventually consistent file system. So what that means is that if you have a Hive query and it writes a bunch of data to a table, maybe like later on you have some other Hive query running in a separate session. If it tries to read data from that table, it may not see all the files. So that's problematic for lots of reasons, but I'll get into that more in a bit. So let's go all the way into the past, Hive 1.1.0, and talk a little bit about how Hive on S3 used to work. The big problem with writing data in Hive on 1.1.0 is that you would basically have to copy data on S3 a bunch of times. Every time you did a rename on S3, that's basically like a file copy. You have to, if you want to do a rename on S3, you have to take the file, copy it to a new location, and then delete the file. And the reason Hive kind of assumes that renames are easy or like can be done very efficiently is that on HDFS they're very fast, whereas on S3 you literally have to copy all the data. So in 1.1.0, that meant for certain Hive queries, you basically had to copy the data 4 times, which is very, very inefficient. When reading data, there was also a lot of performance problems. Just running like a typical like select query, you could end up spending lots and lots of time just compiling the query because it was listing all the different partition locations and trying to get like the file sizes, and you just spent like your whole entire query execution doing S3 calls. So since then, luckily, the Hive and the Hadoop community have invested a lot of time in making Hive on S3 performance much, much better. I won't get into all the details, but these are some of the top-level JIRAs. If you want to go look, on the Apache JIRA, that has like a lot of details. But some of the biggest themes to keep in mind are that when writing data, you basically intuitively want to reduce the number of times that you rename a file. So that kind of makes sense, right? Instead of writing a data 4 times, maybe you'll only just write it twice, right? And any rename that you do, you want to make sure you're doing it in parallel. So there is like a really big bottleneck in older versions of Hive, where Hive Server 2 would basically have to like copy all of the S3 data from some temporary directory to another temporary directory, and that took forever. And the final one is that for queries that use Hive on MapReduce, you want to write any intermediate data to HDFS rather than S3, because if you have like a select query that runs like 10 MapReduce jobs, you don't want to dump all the intermediate data to S3. That's going to be really slow. And then for reading data, a lot of the performance optimizations that were made really focused on making all the metadata operations multi-threaded. So instead of sequentially listing out all the partitions, basically do it in parallel. So what's next for Hive on S3? So I want to touch on one specific piece of work that's going on in the community, and that is commonly referred to as the S3A output committer. So the S3A output committer was recently contributed by the Hadoop community. Basically, what an output committer is that it defines a protocol for committing data to a file system, and the Hadoop community created one specific for S3 files. And the real advantage of this output committer is that it promises to provide 0 rename commits for data on S3. So basically, that means you write your data to S3 once, and then that's it. You can basically commit it, and you don't have to rewrite it or rename it or do any of that like really bad stuff. So to kind of give you an idea of how it works, kind of before the output committer, basically what Hive would do is that each individual Hive task would basically write a file on S3 to a temporary directory, and then Hive Server 2 would commit the data by actually copying all the data from the temp directory to the final table directory. Now, what's really nice about the output committer is that Hive tasks can actually write data directly to the output table, to their final location, and those files will be invisible until Hive Server 2 basically triggers a final commit. And that final commit is basically just like a single network call to the S3 service. So that's one piece of work. It's still very much a work in progress upstream, but it hopefully promises to make Hive on S3 performance much, much better. And that's pretty much all I had. I'll open the floor to Q&A now. Thanks. Questions? Let's go to this.
Are there any similar efforts around the Google Cloud Storage or other cloud provider storages?
Yeah, a lot of the work that we've been doing for Hive on S3, we've tried to make it generic enough so it works for like other kind of cloud storage systems. Unfortunately, a lot of these cloud stores are all very different. So like S3 is like very unique in how it kind of, in terms of its properties. But we're definitely keeping like that in mind. Like a lot of the enhancements we make, we want to make sure they work for other cloud stores too.
Hi, I'm curious about Hive on S3 performance compared to, let's say, Hive on just on HDFS. How much is the gap?
Yeah, so unfortunately I didn't get a chance to collect some performance numbers, but Unoptimized, Hive on S3 is like very, very much slower, like multiple factors slower. Depends on the query, of course. Like if you're writing data to S3, that's like going to be probably your slowest queries. And it also depends on the Hive version. Over the past like year, there's been lots of changes upstream to make Hive on S3 like much more performant. And like we're still continuing to make a lot of performance enhancements. Like the Hadoop community is also really invested in this, so performance is getting better and better every day. But there's definitely still a very big gap between HDFS and S3. I think we're probably out of time anyway, so thanks everyone.
One quick question.
Go for it.
How are you dealing with the data locality? I mean, as we deal with in HDFS?
Yes,
what's the counterpart of the S3 data locality?
Yeah, so with S3, you don't really have data locality because all your reads and writes are going to be over the network, whereas on HDFS, if your task is scheduled on the same data node where your file lives, you get locality. I think there's been some question as to whether that is a big deal or not for S3. I think with networking these days, even doing like remote reads isn't that big of a deal, and if you do have locality, maybe it helps like a bit, but it seems to be not too much.
So does that mean that there's a separate compute cluster which is not doing the data storage? I mean, there is a compute and data storage are two separate things?
Depends on your deployment, but that would be one way to do it. You could have a compute cluster with like a very low, like very slim HDFS data nodes, and it could just be like entirely compute, and you could have like reading and writing all your data from S3. So yeah, you could do that.
Okay.
Cool. Thanks, everybody. Okay, next up, we're going to have some folks from LinkedIn give a talk about Dolly.
Hello, everyone. Thank you for attending. My name is Advait Tumre. I'm going to talk about the data access layer, the DALI that we have built at LinkedIn. The main focus of this talk is to explain how DALI helps us take control of a very complex data ecosystem at LinkedIn. And towards the end, I'm going to briefly talk about future direction for the product. So we commonly see different storage systems being deployed nowadays to manage data. There is online world for handling REST, online world with databases and key value stores, and offline world with HDFS-based access. And there is data that is in flight over Kafka streams. All these systems have different ways of accessing data, different data formats. At LinkedIn, even within HDFS cluster, we have data that is stored in Avro or ORC format, and in worst case, it's mixed if you're migrating from one format to another. So imagine what happens for a developer who is developing application in that case. He has to get a lot of physical details about physical coordinates of the data, develop an application for that, and that deployed on HDFS cluster. All he's looking to do is to access one or more data sets, filter out some rows, transform values. And once he deploys on HDFS, if he wants more real-time experience, he has to repeat all of that for Samza, which is a completely different execution engine. So at LinkedIn, we've designed DALI to basically provide a uniform access layer for this data. What DALI essentially is, it provides a mechanism for defining data sets, a mechanism for storing these data sets, a registry, which is effectively a Hive metastore, a way to access these data sets using DALI readers in different execution environments. And finally, there is a tooling that actually contributes to a very productive authoring and deployment experience for these data sets. So let's look at what a data set is. Dataset is essentially a Hive table or a view, but we augment those views to also capture information about UDFs and its dependencies. So normally, if you're accessing a Hive view that has a UDF, users have to manually register those UDFs. But in case of DALI, those are available directly to the users. System ensures that continuity. So here is an example of a DALI dataset that's defined in Hive Metastore, defined and stored in Hive Metastore. So you can see that it captures dependencies and UDF information. By choosing views at dataset definitions, we basically get two benefits. It allows us to push down common pieces of logic that can be shared across different development teams like data scientists, developers, and business analysts. And the second benefit is it provides a very clean contract between publishers and consumers of data. So publishers can only provide, through views, they can provide access to only the public parts of the data set that they want consumers to depend on and hide implementation details from them. An example is if publishers are publishing data in a particular time format and then they switch to change that format going forward in future, now they simply need to make sure that the view contract is correctly maintained and do not worry about breaking consumers. So how do we access these data sets in different execution environments? So this is a Hive view. How do you make it accessible in Spark or Pig? So typically, we provide a set of DALI readers for different execution engines. DALI reader consists of two basic components. One is a base table readers that accesses data from storage systems like HDFS, and an embedded Hive execution engine that accesses Metastore, compiles the view definition into an operator plan, and then it processes the input coming from DALI table readers to provide an output. Finally, the output gets converted into a target execution type. So this is currently being used at LinkedIn across Pig, Spark, Samza, of course works in Hive. And so the Samza one is also currently getting deployed in a closed beta production environment. To provide a complete picture, so developers typically start by defining their datasets views through Git. They publish their changes to Git. We provide tooling that ensures that all the dependencies are correctly captured as part of the dataset definition. We also provide mechanisms for them to validate and test this in a development environment before they actually get published to production. The views, once they are published to an Artifactory, are then deployed onto a Hive Metastore. At this point, they are available for users to access them in any execution environment using DALI readers. So just to recap, what are the benefits of this approach? What do we gain by having this data access layer? The big benefit is code reuse and logic portability. You don't have to repeat yourself across different environments, and we all understand the software benefits of that approach. We also get to enforce compliance. So now the security features, all the compliance access controls can be pushed down into this dataset access layer. With this, we are also driving an important cultural change within the company where now we can have clean public and private interfaces around dataset. So publishers can have the information implementation, their app-specific information as part of database, but they only get to expose what they are comfortable with to the consumers. That's a very clean contract between publishers and consumers. And now with views, different consumer teams can actually layer these views on top of each other, which helps it easy to build data processing pipelines. So there's one limitation of this approach though. Because we use embedded Hive engine today, we are not able to support joins or aggregations as part of these DALI view definitions. We only support map side operations. And joins are kind of critical in our ecosystem. So we are looking at a new future direction on this product where we want to leverage Apache Calcite and a portable UDF framework that we have developed at LinkedIn. So this will allow us to take logic written for different execution environments, Hive views that are defined, and be able to translate those into a native execution platform. Portable UDFs is a framework that we have developed So if you guys are familiar, like Hive, Spark, Presto, all of them have different ways of defining UDFs, and we have to replicate all that logic everywhere. But with this new framework now, we can author them once and make those portable. This is running in production for Presto, Hive, and there is work in progress for Spark and Samza right now. And the whole ecosystem, like DALI on Presto, is currently supported with this new architecture in production. We do definitely need support for catalog, which is our Hive meta store today. We have a discussion around that, and that's something we are extremely interested in for the future direction. I wanted to acknowledge the contribution of our team, DALI team at LinkedIn, under leadership of Carl and Vasan. And if you have any questions on this.
I have a question. So you said you use Hive Metastore on your setup. So what's the scale of that deployment? Like how many objects, how many partitions? Do you see any kind of scalability problems with Metastore?
We have seen some scalability and GC issues. Do you guys know exact numbers around this?
I don't really know the exact numbers, but I think I may have the slide. I can pull it out if it need be.
So I had a question regarding security. So what level of security is provided through DALI? Is it like fine-grained access control, ABAC, attribute-based access control, RBAC, some of these models? So what level you are providing right now, and what's the plan to kind of provide greater coverage for security through DALI?
It's fairly fine-grained. So basically, dataset owners can define what kind of data they have. So particularly with GDPR, this has been an important factor. They can define this as part of the configuration, and DALI access layer basically leverages that configuration information. The configuration can be expressed as Hive expression. So as a platform, we basically allow them to express that, and once they define that logic, we just execute based on that. So it's fairly fine-grained. So we can obfuscate certain columns, provide a drop, filter out certain rows as required.
Right. Thanks.
Thank you.
Hello, everyone. My name is Vihang. I'm an engineer in Cloudera, and I'm going to talk about parquet vectorization in Hive. So if this gets to work, I can. So before we go into parquet vectorization, I want to kind of briefly go into the concept of vectorization. So what is really vectorization, right? So the top quote in the slide, I kind of copied it from the paper, and I provided the link there. But simply stated, a vectorized code essentially executes like n by w vector instructions instead of n scalar instructions. And the w here is the vector length. So what do I mean by vector instructions? So vector instructions are also called as SIMD instructions, which stand for single instruction multiple data. So modern CPUs, they have published extensions to their instruction set, and these extensions essentially operate using wide registers. So for example, the SSE, AVX2, AVX512, these are all extensions to the x86 architectures which the modern CPUs support, and they work using these wide registers which are 128 of 256 bits long. And the advantage of using these instructions is you can load and process data in parallel using these byte registers. So as a real-world example, consider you have a problem that you want to multiply two arrays, right? These two arrays have long values in it. So on the left-hand side here, you write a simple for loop, and you run through the array, and you do the multiplication one element at a time. So when the CPU support vectorized instructions, and you provide the JVM flag, which is right up there in the right corner, the super word, during the compilation, what happens is this particular for loop gets transformed into something which is logically equivalent to on the right side. So assuming that this particular CPU is supporting AVX2, which is 256 bits, which means that you can load and process 4 long values in parallel. So the loop kind of translates to something on the right. So you are processing four long values in parallel. And this happens transparently, as in like when the code gets compiled, the compiler generates this byte code in such a way that it can take advantage of these vector instructions. So these four instructions, they use vectorized CPU instructions, and they happen in parallel. So you essentially get 4x speed up in this loop execution. So how does vectorization really work in Hive? So let's take a simple example. So consider you have employees table with these 4 columns, and you're running a very simple query, which is given down there. So you're selecting name, and you're also doing a salary plus 1,000 expression calculation, and then you're filtering the rows based on department number. So a typical non-vectorized query plan would look like something like this, right? So you have a table scan operator on the top, which scans the employees table. Now the file input format returns 1 row at a time. So basically, each row will be forwarded by this map operator within the table scan operator, and it will be passed down the filter, select, and file sync operator. So in this case, the processing is done row by row, and the current implementation is in each of these operators, you kind of deserialize the row using the object inspector. So there are a lot of function calls, and there are a lot of if and else conditions, which are not really good for conversion to the vectorized code from standpoint of view. So in order to understand vectorized query plan, I think it's kind of important to understand the different elements in a vectorized query plan. So you have something called vectorized row batch, which is just like a representation of batch of rows. And in Hive, the default size is 1024. And the vector expressions are equivalent to the generic UDFs in Hive, but instead of operating on 1 row at a time, they kind of operate on 1 batch of rows at a time. And similarly, on the vector operators, they map 1-to-1 with select, filter operators, and instead of processing 1 row again, they process 1 batch at a time. So consider this table, right? So we were interested in the name. So this is where column-oriented formats like ORC and Parquet are especially in an advantageous position to take advantage of this vectorizations, right? Because they can select all the column values. So in this case, the name. So you create a name array, right? So you have a string column vector there, which is like a bytes column vector in Hive. And then you select all the decimal values from the salary. You convert that into an array. And then you have department number. You also convert that into an array. And now you have you collect them all together, and that's what is called vectorized row batch, right? So similarly, for the expressions, in our example query, we wanted to calculate salary plus 1,000, right? So this is an example of a simplified example of a vector expression which is doing the same. So here, the expression is picking out the input and output column vectors from the batch, and on the bottom 3 lines, you see the for loop, which is running through the batch and doing the addition on that vector. So if you remember the first few slides of the SIMD, that for loop looks very similar, right? So that gets converted to be able to use vector instructions or the SIMD instructions. So that happens really fast. So the vectorized query plan essentially looks like this now. So you have a table scan operator, but instead of scanning 1 row at a time from the file input format, you're going to scan a batch of 1024 rows at a time. And now all the operators down the line, the filter and the select, they all will be operating on a batch. And all these operators are written in such a way that they can take advantage of the vectorization provided from the CPU. So they all are written in such a way that you have tight small loops without if and if else conditions or a lot of function calls, which will be basically translated to vector instructions. And that's where the performance gain really comes from. So how does vectorization and Parquet kind of relate to each other? So vectorization has been there in Hive for a long time. ORC used to support using vectorized reader, I think, since long time. So since Hive 2.3, the community added support for vectorized readers on Parquet as well. So that's the GR number 14826. If you're interested, you can go online and check it out. So Parquet natively does not provide APIs to get like a batch of column values. So we had to the community had to use the page reader APIs to construct these batches on the Hive source code side. So some of the supported types, like as of Hive 2.3, all the primitive types are supported. I think there is one primitive type, interval day column, day. I think one of the primitive types here is not supported. Struct is supported, but the other complex types are not yet supported. And we also support some basic schema evolution. So for example, you have a table, you change the column type of table, then you need to make sure that when you read from that table, you create the vector row batch correctly. Like you handle the overflows in a similar way the non-vectorized code handles. So this slide here shows performance results. So this is on Hive 2.3, and on the right side, it shows the configuration. So we are using Hive on Spark, and you can see that the blue bars there are on when the vectorization is disabled, and the red bars are for vectorization when it's enabled. And the configuration seen here, it's basically only to test the map side improvement. It does not do any intermediate data vectorization. This is just to evaluate what kind of performance benefits you get from Parquet vectorized file input format. And if that chart is kind of hard to read, this is an easier version of the same chart. You can see the percentage gain for each of these TPCDS queries when vectorization is enabled on Parquet. So you can see that on an average, some queries are like in the range of 20 to 40. Some are giving more than 40%, but on an average, we are seeing about 20% improvement in the runtime on Parquet data. So this is still an ongoing project, and there's a lot of things that we can do to improve. Some of them are like adding more support to complex types. So list, map, union, array, all these, the work is already in progress. I think in Hive 3.0, it's going to be released. We still don't have support for the nested complex types, so that is something which is still we need to work on. And also maybe contribute this code to Parquet projects so that other engines can also use this. In addition to that, there are still some expressions and UDFs which are not vectorized, so we should kind of invest more time and work to vectorize those kind of queries as well. And last but not the least, I'm just here presenting the work, but most of the work has been done by Ferdinand, Colin, Xiao. Shefu did a lot of reviewing, and Matt worked on the vectorization engine itself, and many more from the Hive community. So that's it from my side. If you have any questions, fire away.
On that benchmark page, what was the number of bits that were vectorized?
Sorry?
I'm just curious, in that benchmark, how much vectorization was there? Like how many bits?
How much vectorization was there?
How wide were the registers?
Oh, this one I think was using the AVX2 AVX2 instruction sets. I think it is 256 bits, so maybe four long values in parallel.
So is there a generic UDF API for this, for vectorized execution?
No, so this is all controlled using Hive configurations. So if you look at this slide here, you see the configuration called Hive vectorized execution enabled. That in general is a flag to turn on the vectorization. there are also certain flags for Parquet file format that you need to set up so that it starts using.
No, I mean, how does a generic UDF, the UDF APIs behave when vectorize is enabled?
So the way it works is like you have templates in Hive source code, and when the code is built, you generate the vectorized equivalents of most of the expressions. So when a query is submitted, during the planning phase, you replace all those UDFs to their vectorized expressions equivalents. So in some cases, it is possible that there is no vectorized equivalent, and there are some other ways and there are tricks to do that, but yeah, so if a query can be vectorized, it will be, otherwise it goes on a non-vectorized path.
So what are the cases where vectorization doesn't help, but it in fact reduces the performance?
So some of the cases where, like, it depends on what kind of system you're running. If the system is more network bottlenecked or IO bottlenecked, improving CPU efficiency is not really going to help a lot, right? So let's say, for example, if you have cluster on cloud where you have only less number of nodes and the workload is all bottlenecked on IO and network.
So it has to do with the infrastructure, not to see with what the query is, what kind of the query, what we are running?
Right. So there's one side of the thing where a query can be vectorized or not. So based on what kind of data types are there on the table, whether those UDFs can be vectorized or not, that is one side of the story. And the other side is whether really IO or network is the bottleneck on your system. In that case, even if you improve a lot of CPU performance, you're still going to be bottleneck on the IO or network side. So you probably will not see a lot of benefits there.
And does it have any like more preference towards optimizing things of map side operations or versus reduce side operations?
No,
or they are equally impacted in terms of performance gains?
No, so both the map and reduce side can be vectorized. So these results are only to evaluate what are the gains on Parquet file formats, right? So which are mostly on the map side.
Yeah, that's why I mean, all your plots are map side things.
Right. So, but you see there is a config for enabling on the reduce side as well, and there is a config to change the intermediate data also. So you can tune the cluster so that all the stages of the query are vectorized. So in this particular graph, I wanted to show the benefits of just Parquet vectorization and not just the vectorization in general. Does that make sense?
Thank you.
All right. Thank you, everyone.
Hi, I'm Owen O'Malley. I'm an architect and co-founder at Hortonworks. And I'm here to talk about column encryption. So what is the problem? Hive has a lot of different security models, and so it gets hard to talk about what works in what security model without going through all the different combinations. So we find a lot of our users use SQL Standard Auth or Ranger, or I guess Sentry. I don't play much with Sentry. But so most of the users end up using that because it gives you fine-grained control, right? You can control whether someone has access to the underlying table or whether they can just access the view. And of course, you can use that to either limit what columns they can see or what rows. Unfortunately, that requires Hive Server 2, and that means that you're locked into a Hive world. We also have a lot of customers that want other tools, right? They want to process their same data with Spark or Pig, Cascading, whichever tool they have. And then you only get the ability to control things at the HDFS level, which means you can only protect at the partition level, right? So you can't protect particular columns and say who can see a particular column. You can only see, okay, you can lock off whole directories, which are partitions, but not any finer than that. So why do you need this? there's a lot of sensitive data, and GDPR just made it way, way worse. The first category, of course, is personal identifiable information. Also credit card numbers and medical information. All these cases, you get a lot of regulatory rules about how it has to be handled, whether it has to be encrypted on disk, how it has to be processed. One of the pieces that we were just talking about, of course, is you want to control who has access to this data and what context they have to be in to have access to this data. Of course, if you're going through the Hive Server 2 world, then you can, in fact, get a lot of this control by just controlling who has access to the raw table versus who has the views. But if they have access to the HDFS files, then you're pretty much stuck. And you need column encryption to do that. The other one that you actually really want is to have good access logs, right? The first thing that will happen when someone has a security incident is they're going to pick up the access log to see who read the data and what they did with it. And if you just have HDFS audit logs, you'll know that they read the file, but you won't have any idea if they read the sensitive columns or not. So to do that, we wanted to be able to encrypt some columns, but not all of the columns. So we are setting it up where you can define table properties to say, okay, I want to use the PII key to encrypt this list of columns. You can also have multiple keys encrypting different columns, depending on what kind of data you want. Now, of course, you don't really want to hand your keys off to all of your applications that use it. And so we actually recommend using the Hadoop or Ranger KMS to manage your keys for you. KMS stands for Key Management Server. That way the master key stays on the KMS and never goes to the application. And the program gets a unique key for each file and column that gets encrypted and talks to the KMS. Now, I should say that that unique key is what's actually used for the encryption, so that the MapReduce application, TES application, whichever you're using, will only go to the KMS once for every column for every file. Get that unique key and then go from there. Another feature that we didn't want to mess up, which is important for work, is it has to be self-describing, right? You have to be able to read each ORC file without having any of the data from the metastore be right. And so we did this with encryption too. So the file itself records which key version was used to encrypt the columns that were encrypted and what you need to decrypt it, basically. So therefore, if someone changes that property, right, they decide, oh, Social Security isn't that important, so it takes it off the list, you'll still be able to read your data, and it'll transparently decrypt it for you. Okay, so that's great if you have access. What happens if someone doesn't have access to the key? And Ranger has a nice feature where you can actually set up dynamic data masking. You can say, oh, if Owen tries to read this table and it's between 8 and 5 during the workday, he can read it, but otherwise it'll get masked out with nulls. That's a really handy feature, and so we copied that feature into the column encryption stuff. And so you can define what the user will see if they don't have access to the key. The default, of course, is nullify. Everything becomes null for that column because that's the safest alternative. Of course, and one of the options is redact, where you basically change things based on their character class to a representative value for that. So that's what you often see if you have a credit card and they mask out some of the digits with 9s. Now, the redact mask actually does have limits. So you can say, oh, leave the first 4 characters or leave the last 4 characters alone, but hide the ones in the middle, right? Because a lot of credit card, for example, want you to mask one side or the other or the middle and leave the other ones alone. We also provided a SHA-256, which takes the original value and does a SHA on it and then uses that as the result, as what the user will see. One of the challenges, of course, with that is it's perfectly good, and it lets you do things like do joins between different masked columns, right? So, for example, if you wanted to be able to join on emails, but you didn't want people to be able to see what the email was, you could use SHA-256. The one downside of using hashes for this kind of data anonymization is what happened in the New York taxi data set. I don't know if you guys have seen that. It's a great data set. Basically, every time anyone takes a ride in New York's taxis, it gets a row in this table and tells where they went from, where they went to. Well, when they first did that, they anonymized which taxi it was, but they took the taxi's ID number and then hashed it. Sounds right? Except the numbers are assigned sequentially, so it was trivial to write the program that generated all the hashes and figure out exactly which taxi was giving which ride. So you need to be really careful with your anonymization. And finally, we allow customization. Customization allows you to do things like tokenization, where each user gets assigned a number. The number doesn't mean anything other than the order that came into your system. But please, please be careful with anonymization. It's really, really easy to mess that up. Okay, so now, of course, when we approached ORC, we had the layout of the ORC files. You guys lost my colors. So each column, when you write it into ORC, gets laid out together. And each of the columns get laid out after each other. So column 1 is put up first, column 2 is put in second, and so on. But we wanted to make sure we encrypt both the data and the statistics, because ORC files have statistics that let you find out what the minimum and maximum of this column is, jump around so that you can say, if you tell the reader that I only need to see people who have a salary over $1 million, it'll say, oh, no one in this range has a salary in the right range, and so it won't bother reading any data at all. But all that is effectively the data, so we needed to make sure we encrypt that too. Now, one of the other pieces that we wanted to make sure was that the old readers, right, we wanted to maintain backwards compatibility. So the old readers don't know how to deal with the encrypted stuff. So we wanted to make sure that they, by default, would get the masked variant, while the readers who had the keys and had understood encryption could see the new values if they had access to the key. And ORC has 2 levels of compression. It's got the run length encoding and then the generic compression. So the order that things happen now is you do the run length encoding followed by the zlib, snappy, or LZO, and then finally you encrypt. Of course, if you do it the other way around, you would basically generate random noise, which doesn't compress at all. So you want to make sure to compress first and then encrypt to give as little information to the encryption as possible. Okay. Now I get to geek out a little bit about encryption. Actually, just as a side note, the first program I worked on when I was a high school student back in the early 80s was a encryption program for the Apple II. So I feel like I've come all the way around. So ORC encryption uses AES CTR, which is a standard encryption. CTR has the advantage that it doesn't require padding. Encryption typically happens in blocks of 16 bits or 16 bytes. And so it requires often padding out to those 16 bytes, while the CTR mode doesn't. It also allows you to seek in the data, which was another critical feature that we required for ORC, because ORC can jump into the middle of a block. It's symmetric, which means that encryption and decryption are actually the same operation. And one of the requirements is that you have to have a unique initialization vector for each encryption. So the way that we do it, the program generates a random key IV for each file and column. The KMS encrypts it using the master key, and that generates a local column secret, which then is used as the password. The IV for the actual columns uses the column, what kind of stream it is, the stripe ID, and a counter. And that's used to encrypt and decrypt the data. Okay, that's what I had. Do you have any questions? Sorry, I should have been taking questions as we went. Yeah. See, I was trying to keep on time.
So if there's a column level encryption applied and I have the key, or I mean, I don't have the key, I am authorized user to view a column. So where does the decryption happen? Does it happen at the client side, or where does it happen?
It happens at the client side, so in the task, in a distributed computation. So in the TES task.
Okay, so if I want to do some computation on a column, supposing I am not an authorized...
Then if you're not an authorized user, because of the way this is set up, remember it doesn't force you to run into the Hive execution engine. So if you're not an authorized user, you're just going to get the data that comes out of the static mask. So if
I can't do any computation on the data?
You'll just get nulls.
So what if suppose you're my boss and I am just your employee, and you're asking me to do some computation on a data or a column that is only authorized to be visible to you, but I should be able to work on that data and give you a table with some processed information.
So it doesn't handle that use case.
Oh, okay.
Right.
Okay.
The Hive Server 2 handles that use case, and you can do that with views and UDFs. But no, column encryption won't handle that case for you.
But is there any scope of having to work on encrypted data even if I'm not authorized to view the data?
There are some encryption technologies that work like that. They're still pretty much in the research labs. So there are some that do that, but yeah, they aren't really ready for industry.
Okay, so last question, just in case, if I have the access to a column.
Yes.
And I want to do a computation. In that case, if it's a distributed kind of a query, where would those decryption requests come? Would that happen on each
It happens from the task. So the task will say, oh, I'm trying to read the file. So it'll get the encrypted key for that file and say, hey, KMS, let me decrypt this for me, and it'll give you back the decrypted key.
So who asks for the decrypt? I mean, this is
the task does. It happens inside the work reader.
So, sometimes we save temp files, right, to save intermediate data. What happens to the data, the encrypted data, when it's saved in the temp file?
So the temporary files aren't covered by the column encryption, right? While you're writing the data, you of course have the access to the key, otherwise you couldn't encrypt it. So basically this is for the storage at rest, not while it's in motion. So you'd still want shuffle encryption if you want to make sure it stays encrypted in the middle.
And do you have any performance numbers? What kind of impact it has?
I actually don't have the performance numbers yet. It all depends, though, on how much you're encrypting. Right? If you're encrypting 1 out of 100 columns, it won't be that much. In general, I don't know. I haven't done enough wide. I'm still working on this stuff, so it's still a work in progress.
One last question. Sorry. So there was a mention about the random IV versus the fixed IV that you put. So it looks like the fixed IV is not a good idea. You might have to.
So actually, that's not true. The fixed IV just you need to make sure that you never reuse IVs with the same secret.
Yeah.
And so because the secret was local to the file and the column, it will never get reused outside of that file.
But the generation of AES key itself is not under your control, right? So
you're right that the person who wrote the file is the one who had control, but given that the
sorry to barge in. Can we have this discussion offline?
No, it's okay. It's just a comment.
We are already running out of time.
Sure.
All right, next up, we have a presentation about running Hive at scale at Lyft.
Hi, I'm Sharanya, and this is Rohit, and we'll be talking about running Hive at scale at Lyft and zooming into debugging at scale. So just to give you a really high level overview of our use cases of Hive at Lyft, we use Hive primarily for ETL and batch processing. So that's basically converting all our raw event data into meaningful data models for fact and dimensions, and for also batch querying for the purposes of reporting, dashboarding, experimentation results, and so on and so forth. The scale that we're operating at is our data warehouse size is around 16 petabyte, and we run about 130,000 Hive queries a day. So really quick high-level architecture overview. So our infrastructure is currently on, we use Amazon EC2 for running our services, and S3 is where our raw files sit. So as you can see in this diagram, we've kind of isolated the compute from the storage aspect of it, which helps us with onboarding many new use cases because we can keep also spawning more number of clusters based on the use cases. We currently use HA proxy as a means of scaling out the Hive server 2 processes, helps us to kind of also treat workloads differently. Our Hive Metastore RDS infrastructure is actually shared with Presto. We use Presto at Lyft for ad hoc query usage patterns where query latency is really important. On the left, you can see we have a number of clients that we use to actually connect to our Hive clusters. So what we really want to focus on in this talk is what are the prerequisites for running at scale, right? So it's really important to have the right set of tooling and the config management and deployment setup ready. And that's what really helps you to push any service, for that matter of fact, to production. So this is kind of like the bunch of tools and frameworks we use currently at Lyft for running Hive. And just to give you a really quick highlight, that we're going to be focusing on how these tools have helped us solve one of our most interesting production problems with Hive. So Rohit will be digging deeper into one of the issues we solved.
Thanks, Sharanya. So we wanted to share an interesting debugging story with you. So basically, we that we showed in the architecture, we have multiple HS tools running behind an HA proxy. And we actually ran into an interesting memory leak issue where what you can see in the graph is that within a span of 12 hours, the heap memory is pretty much under control, but the native usage actually goes on increasing up to 60 gig. So this definitely had production impact for us, and it meant like recycling nodes, recycling processes, and things like that. So how did we go about fixing this? So generally debugging a heap memory issue is much easier than a native leak issue. So we started looking at what are the solutions that are available. And one of the options was to actually instrument an alternate malloc implementation called JE-malloc. This is a malloc implementation which comes with FreeBSD, and it's actually pretty much suited for high performance, and it works well when you have a lot of memory fragmentation. It actually helps in that cases. So, but the best part is that it does come with some great profiling abilities. So once you hook up the JVM with JE-malloc, it spits out this nice graph, which you can see on the right-hand side. And it kind of tells you in the native world where is the actual memory being used. And here you can see two big blocks, which is like inflate, init, and update window. And this basically kind of pointed us to the root cause that this is coming from the zlib package. But now we moved on to how do we tie this native methods to JVM methods as such. So generally, so now when we go into this whole fact where we are decompressing stuff, so it's either data decompression or like jar decompression. And we're considering we knew our workloads, we were pretty sure it's related to jar decompression that's happening. And the solution was pretty much simple, like, okay, short-term fix, figure out every jar that's being used by the Hive server as such, decompress it. So jars are just zip files, so you could just decompress it with 0 compression level and use it. And that kind of fixed the issue, but we wanted to figure out the root cause. And what that meant is basically using Visual VM and doing a heap dump analysis. So we kind of went like backward from who's using these inflator classes and then do an invert reference. And then we figured out that we actually, because we do our own instrumentation in Hive and run services, so we actually had some leaks in the session state class. So the whole learning from this is that in case you run into native leaks, JMalloc is definitely a good use case that we had with Hive server, and it helped us fix this. And if you look at the graph now on the right-hand side, you'll see that almost 100% of the resources used by OS malloc, and that's the expected behavior. So yeah, that's kind of what we had. Thank you. Any questions?
Question.
Okay, sure.
So the fix was in Hive code, or like
yes,
did you contribute it back to Hive?
So this was actually considering we run like on top of the Hive, the open source Hive version, we have some custom code. This actually was a result of that, like since we have multiple patches. So yeah, the open source version doesn't have this issue. Yep.
Was that holding a reference to edge catalog jar? Or
sorry?
Was that holding a reference to a UDF jar or a?
It was actually all the jars which is loaded by the Hive server process actually. So it was all the Hive jars which get loaded as a part of the class path. So this is when an actual session is started. The jars get loaded, and then the references are like left after you close the session. So this was actually being held for a long time.
So that's the UDF class loader.
Sorry?
So there's a UDF class loader for every session. Is that the one?
Right.
Okay,
yeah.
Thanks.
This makes it look easy. How hard was it?
Yeah, it definitely took us some time to figure this. I would say the issue went on for about a month of debugging. And the other tools that we mentioned, like benchto and things like that, and able to spawn up clusters. So we would actually run workloads using our benchmarking tool, which is representative of production, to see a similar memory growth, and then do the static analysis, like most of like heap dumps and like even the JMalloc instrumentation where it generates the graph. All of this is static. So you want a representative workload. So it did take some time to do this. Yeah, sure.
So quick time check. We are running late by about 20 minutes. So would appreciate if you keep the questions small and find the speakers later to bug them.
It's okay. Okay, so my name is Jesus. I'm an engineer at Hortonworks, and I'm going to talk about materialized views and the upcoming release of Apache Hive. So this is something that we see very often in Hive, right? When you want to accelerate your query processing and you want to optimize your queries, usually you do it on access patterns. So you have some data, And for instance, you will replicate your data, but you will change some of the data physical properties. For instance, you may distribute it by a certain column or sort it, partition it by date in order to accelerate your query processing. You may filter some rows. So, you have very large tables. Okay, you are only interested in a subset of the data. You may create new data sources that basically are much smaller than the original ones. If you are doing some joins, you have some dimension tables, you have some metrics, you may denormalize these tables. You create a very wide table and you may query this one. You can also, related to that, you can also pre-aggregate some of the data. So you may group by certain dimensions, then calculate some metrics on other columns. So now the problem with that is that users are doing all this manually, right? And then it becomes kind of a nightmare to manage all these new data sources. So for instance, what you are doing is establishing a relationship between the original tables and the new tables. But how do you, if this is not, if the semantics are not like exposed to Hive, how do you know that there is no similar table that has been already been created? Or maybe you have a table that could serve the same purpose. Then you also have to rewrite your queries to use the new tables, right? So if you suddenly decide to create new sources, optimize them in a different way because your access patterns change, you have to point to the new source. You also have to implement some logic to maintain your new tables when the original tables change, and this may mean that you need to fully rebuild your tables because the semantics are not clear. Now, all these can be solved by using materialized views. Materialized views is nothing new. It's been around for a long time in relational database management systems. A materialized view is just an entity that will contain the result of computing a certain query. And there is a very important property, right? And it's that you will establish some relationship between the source tables and the materialized view, and there is some awareness by the system about this semantics and this relationship, right? The optimizer can exploit these views for automatic query rewriting, and also it can handle, for instance, efficiently the maintenance of the materialized view. So it can, for instance, maintain them incrementally, and you don't have to rebuild them fully. So I want to mention, right, that the underlying problem or the concepts, they are not only, the materializations are created in different forms. So it's not only a create materialized view statement. Same concepts apply when, for instance, you have a daemon that will create materialized views based on, for instance, your daily activity, or if you catch a result from a previous similar query, that's also a materialization. Or even within a single query, you may have parts that you can reuse because they will be consumed by multiple outputs of the query. So how does this work in Hive 3? A possible workflow is like that. So you will create a materialized view using Hive tables. They can be currently stored by Hive or any custom storage handler. Up there you can see how the instruction will look like, very similar to a create table statement. And then you can have your user or dashboard sends query to Hive without rewriting them. Hive will rewrite these queries using the available materialized views automatically, and it will execute the rewritten query. So this is, I'm going to be talking very quickly about three parts that will be in Hive 3. The first one, three main parts of the materialized views. The first one, probably one of the most important, is the rewriting algorithm. So what this does is that it will automatically rewrite the incoming queries using the materialized views. It's built on ideas, for those that are interested, that are present in that paper by Microsoft people of 2001. It supports queries containing table scan, project, filter, join, aggregate operators. It also includes some extensions that we have implemented in order basically to make the rewriting more efficient, so you don't have to do, for instance, join permutation You can just extract some structural information from the plan, and you will use this for the rewriting. You can also have partial rewritings using union operators, which means that, for instance, if your view contains data for 2016, and you are querying 2015 and 2016, you can still kind of go to your sources and also read your materialized view and do the proper consolidation. And you can see in that link, you can find more information about the actual coverage of the rewriting. The second part is rebuilding materialized views. So right now in Hive, you will have to do that manually. So you have to basically execute that statement after materialized view rebuild. Now the good thing is that we already support incremental view maintenance. What this means is that you will only refresh the part of the data that changed based on the changes in the source table, so you don't have basically to rebuild the whole view. There are multiple benefits to this. The more evident one is probably that you decrease the rebuild execution time, but it also has other benefits with, for instance, for LLP. It will not invalidate the whole cache, right? Because you are just inserting, for instance, new rows, so you are replacing some of them. So yeah, the cache remains valid when you are basically rebuilding your views. Yeah, the materialized view, in order to do the incremental maintenance, it should use transactional tables, so either micromanage or ACID. And yes, current implementation for the incremental piece only supports insert operations. And yeah, soon we will basically support update and delete. If, when you execute your rebuild, if you cannot execute the incremental rebuild, you will fall back to full rebuild. So that's for that part. And the third part that I'm going to be talking about is how you manage the life cycle of the view. So there are two options right now. First one is you do not accept stale data. So when there is some inserts in the original tables, your materialized view will automatically become invalid and it will not be used for the rewriting. We also have a mode where you can accept stale data. So the freshness will be defined as a time parameter, and how you can think about it is that if the view was not rebuilt for a certain time period that you define in this parameter, and there were changes in the base tables, you will ignore this for the rewriting, okay? And how you can articulate this is that you can say, okay, you know, my time window is going to be, for instance, 10 minutes, and I'm going to rebuild my view every 5 minutes. And that will give you certain guarantees on the freshness of your data and how the system is moving. How long have I done? How am I doing? 1 minute and a half. Okay, I have 3 examples for the rewriting. I will go real quick and I will try to highlight like the main things in them. So this is just to show a little bit the coverage that we have right now, okay? So here you can see a materialized view definition where you have a join between employees and departments, and you basically store all the employees that were hired after 2016, okay? And then you have a query that comes and say, okay, give me the employees and the departments for those employees that were hired in the first quarter of 2018. So you can see that actually the contents of the query are contained in the materialized view. So the rewriting, I mean, I'm showing it here in SQL. This rewriting happens in the logical plan, but so it's more readable. Basically, we can check the filter condition containment, and we add the filter on top. So you will read from the materialized view, and then you will filter only the rows for those employees that were hired in the first quarter of 2018. So that's one of the important parts, the filter condition containment we support. Second piece, this is a more complex one. You have data schema that you can see up there in the right, typical star schema. You have line order and 4-dimensional tables, part, supplier, customer dates. And you can create a materialized view that will basically denormalize this schema and will do the join for all the tables, okay? And then also assume that there are some constraints that are defined on these tables, because Hive 3.0 also will support will support integrity constraints such as PK, FK, primary key, foreign key, not null, and unique constraints. So basically then you have a query that will filter some of this data and will compute a sum on top of it. So there you can see the rewriting that, although the query only uses 2 of the tables out of the 5, the rewriting basically can exploit the information about the constraints and knows that this is a correct rewriting because basically the joins, because of the constraints, are only appending columns, right? You are not altering the number of rows in your source tables. So that's why you can do basically a projection, some filter, you do the sum on top, and that's how this works. And the third example, it is real quick. It's just because I think it's a good example because it's also very applicable to Druid. That is you have a materialized view where you are grouping your data basically by a certain time unit, in this case minute, because you know that you are not going to query data at less granularity than the minute, right? And then comes a query that basically is doing some aggregation on top of it based on the month. So what the materialized view rewriting can do there is to roll up the data. So you read the materialized view, you group the month on top of the minute that you had, and you do the sum computation. And yeah, I think, I had some, you can go to the last slide, it's fine. Yeah. So we have some road ahead. This is like the first version that will contain materialized views. If you are interested in getting involved or anything, just ping me. That link will have more information about what will be coming in 3.0. Right now, if you go, it is basically a placeholder. But before 3.0 is released, you will find all the information over there. So thank you.
So in the interest of time, can I request the audience, if they have any questions, can they follow up with the speaker afterwards?
Sounds good.
Thank you.
Thank you.
Okay, now we're going to get started with the metadata panel. So all the participants, if they could come up to the stage, we're going to start that now.
So the format of this panel discussion would be each speaker will get 5 minutes to talk about the work they have been doing. And once the presentation is done, then we'll open up the panel for questions from the audience as well as the moderator. So Daniel is going to go first, and he's going to talk about Metastore cache.
Thanks, Vihan, to invite me to introduce the Metastore cache. Here, begin me 5 minutes. By the way, can you do me a favor? Remind me every 1 minute. Just kidding. So Metastore cache. So what's the motivation? So first, we get this request first from Microsoft because they have a problem on their Azure database. It's not because their database is slow. Their database performs okay, but they have a characteristic, which is they will throttle the database if you have lots of DB requests in a short time. So we do have a lot of requests in a short time if we run a Hive query. So their throttle actually makes things very slow. That's why we try to introduce a Metastore cache. And also, from a different source, even if you use other database like MySQL, does that help? It helps. It depends on how much time your query run. If your query run more than a couple of seconds, you probably will not notice the difference. But if your query runs really, really fast, what is current Hive is, right? Then you will realize the difference. If a Metastore call, the runtime down from 30 to 40 milliseconds to single digits of milliseconds, then the performance will be noticed. So the major work of cache store is done last year. Actually, by the way, the talk should be by come for this call, but because he is doing most of the research work of cache store, but he cannot come today. So I'm in his place to talk about this. So most of the major work is done last year. This is a server-side cache. So we put that in the server side. What means if you use remote meta store, in your remote meta store, there will be a cache store. And if you use the embedded Hive server 2, if you use Hive server 2, then you will use the embedded meta store inside Hive server 2. So there is a cache store inside your Hive server 2. And by putting the cache in the server side, we can share the most data with lots of clients. So we make best use of the memory. We decide to put every metadata in the memory, which includes all the database, all the tables, all the storage descriptor. Sure, this storage descriptor in the database world, they have a lot of duplication. So for every table, for every partition, we have a storage descriptor which repeat the same information again and again. In the cache store, we optimize this structure. So for most of the table and for most of the partitions, they actually share the same storage descriptor. So we optimize only you will only see one entries in your storage descriptor, and we will put all the partitions. We put all the statistics. When the metastore or the Hive server 2 startup, we will do a pre-warm. So we pull all the metastore information from the database to the memory in one shot. And after that, we'll do time-based refresh. So every couple of minutes or couple of half an hour, we do a refresh completely. And we did a calculation at that time. If you have 10 million partitions, it will occupy 6 gigabytes of your memory. So it sounds okay, right? So unless the use case is very extreme, you will not run out of memory, right? Okay. And also, how do you use your cache store? In your setting, you just set your metastore raw store implementation to cache store instead of the object store. Then you are using your cache store. So in this arrangement, you can have your other cache store implementation as well, right? It's basically another raw store, and this raw store embed the actual object store. So that's how you use the cache store. Next one. Now we get problem. When we put this design in production, we get problem. So the first problem is the memory limit. We said in our original calculation, it seems to be we can put a lot of, most of the use case will fit in the memory. But it comes out another beast, which called NDV bit vector, right? So this is use hyperlog to estimate the number of distinct values. And for every partition, every column, they will use a bit vector, which will occupy 16 kilobytes of your memory, right? So if you do a calculation, if you have 2,000 partitions and 200 columns for this table, and for this table alone, you will take 6.4 gigabytes of memory, which is too much, right? So what's the solution? So first, so 16 kilobytes of memory for the NDV bit vector seems not necessary, because if you shrink it down to 1 kilobytes, we can still get the most of the NDV bit vector. So we shrink that to 1 kilobytes. It's a patch recently put by Gopa. So if you have the same table, it will only occupy 400 megabytes of your memory. And the other thing we try to limit the memory usage is if you have a black list and a white list, you tell us which table you want to put in your cache, right? So if you limit your tables, which can put in the patch, obviously, we cannot do everything in the memory, right? If you have a list query, we have to go to the database to find this information, right? So it will slow down things. But still, we hope this is just some small case. In most use case, you can still fit everything in the memory. And also, the last prevention is if you really have a lot of things you want to read, then we will not run out of memory. We will stop loading the rest of tables if the memory is full. The next slide. And the other thing we want to deal is the HA. If you have the metastore HA, which means you have multiple metastores, and if you also have the Hive server 2, right, then we need to make sure the cache is consistent. Currently, it will be a time delay. So for every metastore cache, you will do the time-based pooling. So in the middle, you will be running out of sync. We don't want this happen, right? If something happens, then the other operation in the same workflow may pull from another remote metastore and get different information. There will be some problem, right? So we decided to use a strong, consistent cache, which means every time you read this metadata from the cache, no matter which remote metastore you are reading, you get the same information. So how to do that? So the approach we are doing is when you write to the metastore, when you write to the cache store, we write to all the places. We write to all the caches, right? So we internally, we actually use a zookeeper, which keep tracks of all the cache store. So once the write happens, it will propagate to all the cache. So to make the cache consistent. All right, that's my talk.
So Alan is going to go next.
Okay, so as many of you may know, there's work going on to actually make the Metastore a standalone project, where it can be used easily with or without Hive. So go ahead and go to the next slide. So let me talk just a little bit about why we were doing this and what it means. Metastore is already used widely outside of Hive, right? It's already used by Impala, by Presto, Spark, and others. We want to enable this. We think this is a good thing for a number of reasons. And we want to make it easier for these systems to use it without being forced to pull in a lot of the rest of Hive. If you just download the Metastore jars pre-3.0, you will get the vast majority of Hive code. And we would like to make this easier for people to use. So what we've done so far is pull the Metastore into a separate module inside Hive. It is still part of the Hive project, but it is actually a separate piece. The only other part of Hive it uses right now is the storage API. So there will be a separate release of it in 3.0, like there'll be Hive 3.0 and there'll be a Metastore 3.0 release. This means that other projects will be able to actually pull just that code in and set it up and run it without needing to worry about the rest of Hive. Why are we wanting to do this? Like, why is this interesting and useful? One, well, actually, let me kind of drive it from a motivational example. There's more and more different pieces going in big data systems, right? And not just Hive and Spark, but also streaming applications, AI, other things out there. What we don't want to see is everybody building their own metastores and then having to try to figure out how to share data between them. As an example of that, Hortonworks has a schema registry that we use as part of our streaming stuff for data that's in Kafka. And right now that's actually in a separate database, which means that our users who are using our schema registry can't see what's going on in the Hive side of the world and vice versa. And we don't think that's a very good story. We want to enable this to be a metadata system for your whole big data system so that your applications can see across what's happening in the different systems, right? So that's why we're working on pulling this out and making it easier for others to be a part of. We also want this to be easier for people who are not part of the Hive project to participate in, right? We have actually had people come to us and say, I'd like to use the Hive Metastore for what I'm doing, but I'm not part of Hive. Are you guys going to pay attention to me? Do you care? Are you, will you be responsive when we want to do things? Because we're going to want to do things Hive doesn't want to do. By separating it out a little bit, we make that easier for those people who aren't part of the Hive project to still come and participate in the project, which is part of the way Apache works. So I mentioned that we have already done this separation in 3.0, that it is separable, but we worked very, very hard to maintain backward compatibility. So for clients, if you have an old client, it should still run against the new system. We didn't change the thrift protocol in a backward incompatible way. We didn't make any of those changes. Now, if you write hook implementations in the Metastore server, there were some small changes that you will need to adapt to, but they're pretty minor. They're things like the configuration class changed because we couldn't use HiveConf anymore because that's part of Hive. Okay, go ahead to the next slide. So wait a minute, haven't I seen this before? Didn't you call it HCatalog 3 or 4 years ago or whatever it was? Or are you just telling me the same old thing again? No, we're not. This is actually different, even though it doesn't sound different. HCatalog focuses on making the Metastore available to other systems, MapReduce, Pig, etc. It includes metadata access, but also the whole data access layer, right? It is a data access layer, similar to what the LinkedIn team talked about a little bit ago. It's a very similar product. That is not what we're building here. We're not building a full data access layer. We are just trying to make the metadata catalog separable and usable by others. The way to see this is the Metastore stores information about how to access the data, like what SERDI should be used, but it doesn't provide you those readers or writers, whereas something like HCat actually provided a set of readers or writers. So HCat is actually staying with Hive in the split, not going with the Metastore, which I know is a little bit funny. So then the next obvious question is this going to stay in Hive or is it going to be its own project? Is there going to be an Apache whatever? That's still an open question that we're discussing in the community. And so we'll see where that goes, but we decided we would start it first as just something separable inside Hive and then continue the discussion from there. I don't know if I hit my 5 minutes.
Thanks, Alan. So Parna is the next speaker.
Hello, everyone. My name is Parna, and I'm a tech lead in Cloudera. And I'm looking into metadata and how the metadata should be enhanced in the future. Working very closely with some of our top customers, looking at what are the problems that people are facing today with metadata. Right? This is a typical workflow that we see in most of our top customers. Right? We have an ingest phase. We have a data curating phase where you process your data, you take the raw data, convert it into a consumable set of data, create data lakes for the applications, and then you'll have the applications pull the data from there. Right? And most of the times what we see is that Hive and Spark are prevalent platform for doing the data prep part of it, and Impala is being used specifically for the speed with respect to querying the data. Right? Now, it's a nice diagram, it's a nice flow. I mean, it seems it should all work, right? But it does not. And there's a lot of challenges that our customer face today, right? Anyone wants to take a guess of what are the challenges that maybe here that people may be facing here? Anyone in the stage as well? Okay, you can go to the next one. Very simple ones. Crashes. Go back. Yeah. Crashes. We see crashes all the time, right? And why does this happen? So I've been working on this one for the last few months, trying to figure out like why are these things so brittle in customer setup where when we test it or when we look at it, it seems all fine, right? And it turns out there are 2 or 3 specific things that are there. And if you can go to the next one, one of them is large metadata. We have been talking about big data, but we have a big metadata problem, right? We have 70,000 tables. This is one customer, one cluster. We have 70,000 tables. We have got 2.4 million columns. Guess what happens if we pull this information into any of the processing engines? Right? And in parallel, because we don't do everything is all happening in parallel, right? The same customer has done 2.8 million Impala queries within 1 month, right? The next one. Let's go to the next one. Small files. This is a prevalent problem everywhere. We create our ingest process. We tell users to just ingest the way they ingest it using Scoop and doing the Hive. This particular customer has 36 million files in their HDFS. 14.7 million files are less than 100 kilobytes. How did it turn out? What question comes out is, sorry, what happened? Nothing's coming here. So now this customer's question is, what do I do? How do I go and solve this problem? Right? And where do I start? Right? The third one, let's go look at it, is a handoff problem. And a lot of this thing actually derives from this handoff problem, right? We have this phase where we are using different tools at different times, and the data is getting ingested in a very rapid way, right? When we're ingesting data in a rapid way and we want to query as quickly as possible, there is this impedance mismatch between ingest and the data prep and the query. How do we match that? Like in this example, right? Like Impala basically takes a cache of the metadata, whatever is the cache. And from Impala's point of view, the metadata doesn't stop at the partition level or the directory level. It goes down to getting the file information and the block information. Now imagine with a small files where you've got thousands of files out there, you're going to keep gigabytes of information per table, right? That happens, but still, user wants to refresh their cache because they don't know when the latest data is arriving or what is the logical checkpoint for my last data. They're doing these things again and again, and they're doing it for, to make sure that the queries run fine. And what happens with that is we add super heavy load on name node, we put super heavy load on HMS, and both of them just are not scaling up. And if you go further to this, if you go to the cloud environment, if you go to the multi-cluster environment, this problem is just waiting to explode right now. So my request to the community here is that as we go forward with a different set of metadata changes, right? You can go to the next one. We need to consider the entire ecosystem. We need to consider it across all the different processing engines, across all the different types of users, and as Alan mentioned, it's not just SQL-based metadata, right? It's non-SQL based metadata as well, right? Like what about Kafka schemas, or what about edge-based tables and stuff like that. So we need to consider, as a next generation of metadata iteration, we need to consider a much bigger picture when it comes to developing that. Thanks.
So now the panel is up for questions. We started 10 minutes late, so I'm hoping everybody is up for staying 10 minutes more. So while the audience thinks about questions, let me start. So Alan, my question is to you. So you talked about HMS separation and the motivation. So how do you see, how do you project, 2 years from now, what do you see happening in the ecosystem with respect to HMS? Do you see more and more projects having more standalone deployments of HMS?
Yeah, that's very much our hope, right? And so I think by getting it out of being just a part of Hive, we enable not just this wonderful slide that you can't see.
They can.
Oh, it's back up. Good, excellent. Where all these can use it, but also more and more different types, right? Streaming data for Kafka. What other things as they come along? We would like to see this really be the standard way people store metadata in the big data world, right? So that they can interoperate. And that's not about, oh, we've got to be in control of everything. It's about we want users to be able to interoperate with their data wherever it is, not be tied to, oh, my data is in this system, so I can't understand how to get to it. But rather, maybe I wrote the data with Spark, but I want to read it with Hive, or I wrote it with some streaming thing over Kafka, but I want to read it with Presto. All those systems should be able to interact. That's where I hope to see this going.
Yeah, I think that makes sense. So
So in lot of, again a question for Alan. In the HMS API calls, there is like a very strong coherence between like the persistence of metadata and also file system operations. As part of moving outside of Hive, are you also thinking of separating out those two, like, or what is there any planned course of action on that?
So let me make sure I understand what you're saying. Are you saying as far as how it's physically stored, or do you mean the fact that the metastore itself actually makes a lot of calls down into the file system?
The metastore actually, the second.
Okay. At the moment, there's no plans to pull that apart. We have had discussions about whether we should think about that, but so far we haven't. We're just worried about, okay, let's take what there is and pull it out. The thing is, having HDFS as a representative way to access the data is pretty good because it can work over local, over HDFS, over S3, whatever, right? You can still get to the data. The question then becomes, how much should we abstract away physical storage properties at all from the metastore? How much should it just be logical metadata, and how much should it know about the physical stuff? And that's a debate we haven't had yet.
Thank you.
So the next question which I had was for Parna. So you have seen a lot of customer cases, a lot of actual support requests, and not just for Hive, but also for other components which are Hive Metastore clients. So in your experience, what do you see the HMS API to be sufficient? Do you see some drawbacks? Do you see some systemic problem with the APIs that are related to those scalability issues, or?
Yes. So one of the things that I've seen, at least, and is that the Hive, the current HMS APIs are way too chatty. Like, for example, today, if you look at the way Impala does its partition pruning, it does its own partition pruning. So it needs to pull the entire partition information. Now, if you have a large table, that could be a lot of partitions. Right. Similarly, if I'm in the semantic analysis phase, I have to figure out, okay, what are the tables and the columns for this thing? Depending on how many tables I have in the query, for each query I have to make that many RPC calls. Right. Potentially, some of those things can be improved, and I think a lot of scalability we can actually achieve a lot of scalability, and especially with caching getting added, with changing the APIs to match more with what actually the processing engine wants. We give primitive operations from HMS today, but a more upper level APIs could be quite helpful in that case.
Okay, thank you.
Yeah. So Alan, you mentioned that when people were integrating with HMS, one of the concerns they used to have is whether they will get enough attention and the right kind of support and things like those. What are some of the instances, and what is your way to kind of go back to those teams or the new ones who might be integrating to say that now this is a separate project and therefore you will definitely get more attention? It's essential for this success of this project itself.
Well, it's not so much about attention, it's about ability to come join it, right? I mean, in Apache, you don't get attention, you come and contribute. And I think, at least, I will use the one example I'm the most familiar with because it's internal to our company, of building our schema registry, right? When we started looking at building the schema registry, the team was interested in, can we use the metastore? We looked at that, and one of the things that they were concerned about was, we'll never be Hive committers because we're not contributing to the core of Hive. We're not writing new storage formats or query optimizations or whatever. We just want to mess with metadata. And so they were afraid they'd never be kind of let in the door, if you will. And so I think that's the key, where now we can go to them and say, look, metadata is what we do. So if you want to be a part of that. Now, I think it's also, by pulling it out, we enable one other thing, which is, today the Hive Metastore is very focused on thinking about things from a SQL point of view. We have tables and partitions and views and databases. That's not the way, if you look at Kafka-based streaming systems, they don't think about tables and views. They think about topics and schemas, and every message in a topic may have a slightly different version of the schema, and they have to handle that, things that we don't ever care about. So part of this is enabling the people to come to it, but part of it is also us being open to saying, oh, that's another valid way to think about data, and how do we make it so the tools can cross-connect, right? Because if you do allow these Kafka streaming systems in, they have to be able to view the table data in a way that makes sense to them. But at the same time, you want the SQL engines to be able to come and say, oh, well, how do I look at that data in a topic, knowing that it's not really quite a table, right? So I think it's on both those sides.
Awesome. Is that the pitch for separating it out into a top-level project?
Yes, it is.
Thanks.
An unabashed pitch.
I have a question. We talked about the cache in Hive, and we also know that Impala caches. Now, when we separate out HMS, we don't want every single component to build a cache, right? So are there any plans to, address that aspect?
Yeah, that's right. So and didn't look at the Impala cache. I'm not sure it's server-side or client-side. So when we design the cache, we intentionally make it the server-side so it can share across different components. So once we have Metastore as a separate service and serving all the components, we definitely want to look at this aspect. We don't want to replicate the logic into different projects.
And the cache is in the Metastore already. So when we pulled it out, the cache store went along with it. So that's already, we're kind of 90% of where we need to be with it.
There are some concerns about Thrift being slow, and I think Impala pulls it into the client side, right? If I'm
yeah.
Yeah, so are there any plans to improve the Thrift side of it?
There are raging debates, but no plans. So I think there's an agreement that the current interface is a spaghetti disastrous mess, right? Because it's not just that it's Thrift, it's that there's 37 ways to fetch the partitions. That's 40? Okay, sorry, I undercounted. I don't think anybody thinks that's optimal. But once you open that can of worms and say, okay, well, let's make the API work, the first question is, should it be Thrift? Should it be gRPC? Should it be REST? And you can find somebody to argue for each of the options, and then how do we design it? So yes, we know we need to do it, but it's one of those things we've pushed out in favor of getting just a separable, viable service, and then we can start talking about that. Because one of the hugest questions there, if we do redo the API, is we have to do that in a way that gives people a progression, right? We took great pains to keep this backward compatible because we don't want to pull a Python 2 versus 3 kind of thing where people just don't upgrade, right? That would be very bad. And so if we do decide to rework the API, how do we do that in a way that's still supports the old one and gives people a migration path? Right?
One more thing I would like to add is that, as Alan mentioned, that API design itself, right, like could change the game with respect to speed. If you can reduce, if the API design can help reduce the number of RPC calls that we do for each of the operations from the processing engines, that itself is a big win. And, with that, we can add whatever underlying mechanism or underlying protocol for serving the APIs.
I just want to add in one more thing to the Impala's cache. If this is client side, there's nothing to prevent the client side at another layer of cache, right? Server side cache has its own responsibility, and the client side cache can exist in the same time.
I have a question actually for the caching side. Sorry.
That's my job.
So the question is like, we are building our own caching layer in HMS right now, right? Like, was there any study done or any thought about using one of the standard ones that exist? But there are many of these caching layers that are coming up, like Hazelcast or Infinispan, or even just using Memcached or something like that, instead of building the whole thing ourselves.
Yeah, we actually thought about it last year when we implement that. So we referred to Presto has a cache, and I don't recall the other things we studied. But first, we don't want external server like the main cache D. We don't want another external server because in the cluster, the management will become a huge problem. So we want that to live in the metastore itself, not everyone talk to another external server. And we want to serving all the requests. Like Presto Cache, they have a ARU. So they will evict the things least frequent use, right? So you will not cache all the partitions in your memory. You only cache some of the partitions. But the problem is you can answer some of the requests, but not all the requests. Like if you want to list all the partitions of your table, you will not be able to do that within your memory. You have to go to the disk. So that's the things we want to avoid. But sure, that over the time we will see other new things come out, which we probably overlook in the past, or the new things come out we have not yet looked at yet. But the cache store itself is just one implementation of the raw store itself. So it opens the door to other implementation of the cache store if someone better comes in. So I actually have another question for you. so when you say Impala cannot use the predicate pushdown of the Hive metastore, is that because of the interface, which is not convenient for Impala?
That's right.
Okay.
Right. And this is what we are thinking about. And that's why we're thinking about like the next set of APIs that we think about, right? Like how do we map, the three phases that are required, right? Like the semantic layer with the planning stage versus the task assignment stage, where you need the file information or the location information for assigning the tasks. So between these three phases, right, how should the APIs look like? So so think about like what HMS is providing today is like all the primitive APIs, and beyond that, if you want to start providing a higher level API which can help all the processing. I'm not talking about just from Impala's point of view, but from Hive, from Spark, from everyone. What could be that common layer of API that could give us, solve some of the scalability problems with respect to with RPC calls?
I think there was a question in the audience.
Yeah. Hi, Alan. This may be a question for you. So one of the things in LinkedIn we sorely missed in the Metastore is type support for complex data types like structs. So give you an example where this is really biting us. So with DALI, we define a lot of data pipelines with views. And you can think of a view which could be unioning two tables. And they would have the same struct, but not as a type, but as anonymous structs. And as the tables gets updated, the structs get changed at different times and a view pipeline breaks. And we have some hacks to overcome this. But I just wanted to know if there's interest in the community to support something like types for complex data types. And this may be similar to like the schema registry work that you guys are already doing by adding that information there.
I am not aware of anybody doing work on upgrading the complex types in the Metastore or the complex type support. That said, we are certainly hearing people express interest in better support for structured data types like JSON and those sorts of things. So your patches will be very welcome.
Thank you.
That's the best answer. Your patches are very welcome.
We have a question from Slido from Donald Trump. Currently, Metastore mixes up concepts of true metadata, schema, location, etc., static data describing data, with runtime info, which query engine needs, like asset transaction stats, etc. It seems like this should be managed in two different systems. Thoughts?
Okay, so sure, theoretically it should be in multiple systems, but realistically when you start splitting things across systems, what you're doing is creating an administrative burden, right? So I'm not, Mr. Trump there is not the first to suggest that we should be splitting up the logical from the physical, or even that we maybe should split out the the metadata from the transaction system, which is also in the Metastore, or other pieces. My personal take on that would be, well, twofold. One, even if we want to split those things out in terms of servers, that doesn't mean they don't all reside in the metadata system and don't make sense to be shared between different systems, right? I don't think we have a situation where there's other, like random bits of goop in there that only some people will care about. I do think we have a system that most everyone will need to know stats, transactions, the table definitions, all those things. But then I think you only want to pull the servers apart when the load requires that you do, because otherwise you're just adding systems for your admins to deal with, for your for people to install and all that stuff. So I don't think you want to just willy-nilly pull things apart.
Okay, I think we are about to run out of time, so we'll just take one last question.
Okay. This is regarding metadata caching. So you mentioned HS2 also in the embedded mode can do the server-side caching. And at the same time, you also said on the HMS, there is a quorum, zookeeper quorum, which maintains the consistency by talking to each other. So how does this work? Because in general, HS2 has a different quorum altogether, right? It doesn't generally be part of the HMS quorum itself.
So first, this is a work in progress. It's not done yet. It's not in the Hive code base. Second, I mentioned something in a footnote last when talking about it, probably didn't catch. So we actually have a zookeeper, right? So every cache store, no matter this is a remote meta store or this is a Hive server 2, as long as it's using the cache store, it will register itself into the zookeeper. So the new zookeeper have the tracking of all the cache store. So every time if you want to update, then you will find all those nodes and write through every cache.
Sure. That makes sense. Thank you.
Thank you.
So I have just one last follow-up question on that. So for the cache store, like at least on the object store side, right? It's based on my understanding, it's a thread local, which is on the HMS handler side, like on the server side. So is cache store also instantiated like that? And does that mean like you have multiple caches in HMS?
It's also thread local, but it's a singleton, right? So all the cache is in it's a singleton, but the cache store itself, which probably just a very small class, it has the virtual points to all the methods. This is thread local as well. So this is just a raw store. So it's the normal way we instantiate the raw store. We will instantiate the cache store. But the cache itself, which is the big memory part, it's the singleton.
Okay, that makes sense. So I think we are much above the time limit. So and I see tired faces in the audience. So we'll call it a day. Thank you everyone for your time and patience. Thank you for all the speakers for their time. And we'll see you next time, hopefully soon enough. Thank you.
I didn't see that code in there when I was putting the catalog in.